So let's do an example. But before that, we said system has several properties. We talked about 6 properties, which were memory. And we said the system is memoryless if it
does not depend on the previous
or future value. If the output at time t depends on the input at time t, then we call it memoryless, otherwise it's with memory. Then we talk about invertible. We said the system is invertible if
there's always only one output for one input.
Yeah, for a distinct input we have a distinct output, unit input, unit output. Or if it was a function of if it's a one-to-one function, then we call it invertible. Then we talk about causality. What was causality, Abdulaziz? We said all the systems that we have in the real life, they are all causal. Ulari, what's causality?
The output depends on either the input at the same time or the previous one.
Okay, yeah, the output depends on the time at now or and previous values, but it never depends on the future value. And what was the stability, Ozan?
I don't remember.
We had a very special term, BIBO, which means
A boundary.
bounded input, bounded output. If we give a bounded input, we get a bounded output. And we said bounded. And how do we define a bound? Limit. Sorry?
Magnitude.
Yes, we put a limit on the magnitude. Magnitude-wise, it is bounded, not time-wise, because we always start from minus infinity, we go to plus infinity. And then we said we have 2 more properties which are very important. One of them is called time invariant, which means
Basically, it doesn't depend on the time.
no, it doesn't depend on the variation or translation of the time. It doesn't depend on time, it's different. Now, it means that if I shift the input by t0, the output will be shifted by t0. And we said that the event itself does not depend on time. And I gave this example. I hit the board, we hear this, and if I do it 10 hours later, we hear the same sound. So it means that this event is time invariant. And we said that in the reality, lots of things are actually time variant. Like even if I do this, and if I do it again after a few seconds, although we hear the same thing, but we understand because of the first hit, the molecules are still shaking, so the distance between the molecules are changing, so the frequency produced is not exactly the same. But easily, without having any loss, we can approximate it with time invariant. And then we said we have one more property which is called linearity. And what was the linearity, Ozan?
Like input values depends. I think I can show on the formula. I cannot explain.
Yes, I mean in that formula there are 2 important things. And those 2 important things is that we have the scalability or homogeneity. In other words, if I multiply the input by alpha, the output will be multiplied by alpha. And then we have additive property, which means that x1, if x1 gives us y1, if x2 gives us y2, x1 plus x2 gives us y1 plus y2. And if these 2 conditions are verified, we call it that it is a linear system. And we said that in the reality, almost all the systems that we have are nonlinear. But most of those nonlinear systems can be approximated with linear systems. That's why that we are studying these linear systems. And we said if the system is linear and time invariant, we call it LTI systems. We didn't talk about it, did we? I will talk about it in a few seconds again. But before that, let's do an example on linearity. And it is this. Is the following system described by, we said that when we have a control system, we describe it by a model which is basically a differential equation. By the differential equation y dot t plus t yt is equal to xt linear. Note, dot means derivative with respect to time. So y dot t means dyt over dt. Okay? So we can easily understand that y double dot t means d squared yt dt squared, which is the second derivative, right? Now, okay, 2 minutes to you. Think about this. Is the following system linear or not? Maybe you want to do it in your notes. Is it linear?
I think it's not linear.
Whether is it linear?
I don't know.
So in order to see if a system is linear or not, what we do is this. We say that we assume that x1t is resulting to y1t and x2t resulting to y2t. And then we check if alpha x1t plus beta x2t is resulting to alpha y1t plus beta y2t. So what we have to do, we have to check this one. Let's see. x1t is y1t plus t y1t. And x2t is y2 dot t plus t y2t. And alpha x1t plus beta x2t is alpha y dot 1t plus t y1t plus beta y2 dot t y2t, which is alpha y1 dot t plus beta y2 dot t plus t dot alpha y1t plus beta y2t, which, if we call this one y3, it will be y3 dot t plus t y3 t, where y3 t is the input of is the output of x3t, which was alpha x1t plus beta x2t. So hence the system is linear. So the system is linear. What about a system? What about it has a special name. It's called a squared law system. What about the S squared law system? Is it linear or not? And the system is this: yt is xt squared. So the question is that, is this system linear? Yes, Thomas. Or Martin?
It said it's square. It can be linear.
It cannot be linear. So it's very easy to see that this is not linear because it's parabola, right? It's parabola. So but you cannot say that, oh, because it's a square, it's not linear. You have to show it. We know that this is not linear, but we have to show it. And let's say assume for x1t we have y1t, which is x1t squared. For x2t we have y2t, which is x2t squared. And for alpha 1 x1t plus alpha 2, let's call it alpha and beta, so we keep the consistency of x2t. Then we have y3t, which is alpha x1t plus beta x2t, the whole thing is squared, which is alpha squared x1 squared t plus 2 alpha beta x1t x2t plus beta square x2 square t, which is obviously is not alpha x1 square t plus beta x2 square t, which was alpha x1 and alpha x2. Now, these linear and time invariant are very important because a system which is linear and time invariant is called an LTI. L means linear, TI means time invariant system. So a system which is linear and time invariant is called LTI system, and from now we are dealing with LTI systems. Such system can be characterized with its impulse response. So such a system can be characterized by its impulse response. What is impulse response? What is impulse response? Come on, everybody has taken this DSP or signal systems.
You basically give pulse to input and watch.
Yeah, impulse response means the response of the system if impulse is the input. So this is the output or response of the system if the input is unit impulse signal. And we usually show it by HT. This is very important because by finding the Laplacian of HT, we can obtain transfer function of the system. If we are finding the Fourier representation of impulse response, what do we get? Frequency response. And if we calculate the Laplacian, we get the transfer function. What is the difference between the transfer function and an impulse response?
One is in the frequency domain, and the other one is.
One is it? Yeah, they are in different domains. The difference is that they are in different domains. Now, if we have an LTI system, we can characterize all the properties that we have by using this impulse response. And one of the most important property that we can get from the LTI system is that for any input xt, the output is the convolution of the impulse response by that input. You may remember this one. And again, if I tell you that we have an HT for LTI system, by looking at that one, we can understand if the system is with memory, if the system is stable, or causal, or invertible. If I give you the HT of an LTI system, how can we understand that the system is with memory or memoryless?
Differential, if like S square means it depends also the past values.
If I give you HT as a function of time, when you look at it, how can you understand it's memoryless?
If there's T.
Look, HT is impulse response, right? And memoryless means that at time T, I only depend on the input at time T. So it means that the input should be of the form of delta, like yt is equal to constant k multiplied by delta t. Yt is LTI and memoryless if, in general, yt is k multiplied by delta t, multiplied by xt. So, this is the general form. So, how HT will look like? What about HT? This is the definition of the memoryless, right? Output at time t depends on only input at time t. If I write here t plus 1, t minus 1, I'm with memory. So this is the general definition. Now, tell me, what is the impulse response? What is HT? Definition of impulse response means the output of the system if the input is impulse. So if the input is delta t. So a system is memoryless, the LTI system is memoryless if its impulse response is of this form. Otherwise it is with memory. So if you have HT is equal to K UT, this is with memory. Being with memory is not bad. We can practically have it. Actually, most of the systems that we have, we are using some integrator inside it, and we have already memory. So, I mean, having memory is not bad. What about causality? Now, this is a question that I want you to think, and then I ask every single of you, and I want to see what is your comment. This is delta t, right? What is the definition of causality in general?
Depends on the present.
The present and or past. In other words, nothing of the future. Nothing of the future. I will give it to you, listen to me. So, I should not depend on the future at all. Now, tell me, what should be the property for impulse response, for HT, that if I look at it, then I can say that the system that I have is, what's called? Causal. So what the HT should look like, that when I look at it, I will understand that the system is causal. In order to answer it, keep this one in your mind. Causal means I do not see the future, And impulse response means the input is delta t. So these two information should be enough for you in order to come to the conclusion how HD should be looked like. Let's say, think about it for a minute. So who wants to be the first victim?
Maybe there's we can say that maybe k delta t times delta t minus maybe a constant, which is it could be a delay or something, which is like the previous.
No. Note that this is for memoryless. If it is like this, definitely it is causal, but this is not enough.
So delta t shouldn't be on the right side.
Delta t should not be on the right side.
On this, like, shouldn't be t plus 1, t plus 2. It should be t or t
No.
minus 1.
No. I can understand that you remember something, but you remember something wrong. Okay, Thomas?
I don't know.
Larry? Okay. So, think. I am causal, which means that I cannot see future, right? I can always look past. So, and I know that delta is always 0, except that I am at 0. So when do I, and imagine that here, on my right side, your left side is minus infinity. And I am a causal system, which means that I am always looking at this direction, because I can see past and current. I cannot see the future. So can you tell me that where do I start to see the delta? Because here I am 0, I see 0, and I don't know. I mean, 0 can be unit step, 0 can be any function.
So we should inverse it?
No. You tell me this, you answer this question. I start from minus infinity, and I'm going towards plus infinity, but I can always see past. When do I start to see the delta?
Past 0.
Present.
If I am at 0 or past 0, because if I'm at 0 I see the delta, and if I pass 0 to plus infinity I can always see it. Right? Okay, this is good. So, before I come to 0, I do not see anything except 0. So if there is no, if their input is 0, which means there is no input, what is the output?
0.
0. So in other words, the impulse response before I come to 0 is 0. Why? Because impulses start to happen at time 0. I don't see anything. So impulse response 0, impulse response 0, impulse response 0, till I see the impulse, then impulse response happens, and from now on I can have some value, because I can see delta always to plus infinity. So this means that an LTI system is causal if HT is equal to 0 for t less than 0. Why? Why it should be 0? Because the input is 0 and I have no input. And if I have an output, in other words, if HD is not 0, it means somehow I can see that there is an impulse in future. So somehow I am grabbing something from future, which means then I am not causal. Now, and we know that such system does not exist. All the systems that we have are causal. So you turn on your filter, there is no input, but you get some output. What is that output? It's a noise. Because we know that the system is causal, and when you have no input, you should get no output. If by any means you get an output when the input is 0, it means there is some noise or some problem in there. But in general, no input means no output will happen. And that's why that, because when t is less than 0, the impulse has not happened yet, and I cannot see it, so it means the impulse response is definitely 0. Now, what about, what was the other property? Stability. Because, you know, when we say that we have an LTI system and the impulse response is HD, this is very important. You do not need to talk about anything else. You just give me what is HD, I can calculate what is the output for any input, I have to be able to tell what are the other properties. And one of that properties is stability. By looking at HD, how can we understand that the system is stable? Is this. If integral from minus infinity to plus infinity of absolute of h tau, d tau is less than infinity, then we call the system is stable. Then LTI system is stable. Do you know in mathematics what do they call this? If integral from minus infinity to plus infinity is less than infinity, in other words, if this integral is a number, we call it is integrable. And in case of discrete time, we have summation k from minus infinity to plus infinity of absolute of hk, it is less than infinity, which means that the impulse response is summable. Maybe the sum is 1 billion, but it is a number. So if this happens, it means that we are stable. Otherwise, we are not stable. So it is very easy to see that e to power t, is it stable? Integral from minus infinity to plus infinity of et dt is e to power t from minus infinity to plus infinity, which is e to power infinity minus e to power minus infinity. This is 0 is equal to e to power infinity, which is infinity. So this is
Not stable.
not stable. What about e to power minus t? Is it stable or unstable? Lozan?
Like this, it is minus infinity, and
It's integral from minus infinity to plus infinity of absolute of e to power minus t. I mean, we have the absolute, but here we threw it away. Is equal to absolute of e to power minus t multiplied minus from minus infinity to plus infinity. It will be absolute of e to power minus infinity minus e to power infinity, which is absolute of minus infinity, which is infinity, which is not stable. What about, let me write these ones here. What about e to power minus t ut? It is the integral from minus infinity to plus infinity of, let's put the absolute also, e to power minus t ut dt. But what is ut? Sorry? Unit step function, but what is its properties? What does it mean? Yes?
It's just an odd number.
It is just?
An odd number.
It's just a number.
Like that.
What is unit step, Ozan?
Like before t, it's 0. After t, it
What
is
is t?
time.
No. You are right, but there is one mistake. What was unit step? Come on. Don't break my heart.
Smallest.
It's a step function. What Ozan said is okay. It's 0 and then it is 1. But at which time
Current
this
time.
step happens?
Current time.
At time 0. ut is t less than 0, t greater or equal than 0. So, from minus infinity till 0 I am 0. So it means the integral will be 0. Right? Right, Abdulaziz? Look, from minus infinity to 0, ut is 0, so I have an integral 0 dt, plus from 0 to plus infinity, what I have, this is 1. So it's e to power minus t dt, which this one is 0. So I have absolute of integral of e to power minus t from 0 to t dt, which is absolute of minus e to power minus t from 0 to infinity. The absolute will kill this minus, so I have e to power 0 minus e to power minus infinity. This is 0. E to power 0 is 1, so the result is 1. Right? So what do we understand? Is it stable or unstable?
Stable.
It's a stable because it's a number. So this one became stable.